Now we're going to try to see a simple modification to this algorithm will make it run in expected linear time. So have this algorithm in mind with two steps, initialization and the for loop. We add only one extra step. We add a next step between initialization and the for loop. And this step is just to randomly shuffle constraints. In other words, if the constraints are given to me in some order in the input, just reorder them. And that's it. And then run the exact same algorithm. Another claim is that this algorithm runs in expected linear time. This sounds magical, and there's actually a theory that explains how and why this happens in general. But here we're going to look at a particular proof, or a proof for this particular claim. The proof follows a very interesting technique called backwards analysis. I'm going to give the proof in two steps. First, we're going to assume this main claim of the backwards analysis, and then we're going to prove it in the next video. So what we can assume here is that we assume that the step 3.2 runs with probability 2 over I at the ith iteration. What this means is that if I just zoom in the ith iteration, so let's say this is the algorithm is running, so there's iteration 1, there's iteration 2, I only care about iteration I. I pick a fixed value of I and I just look at this. I look at the ith iteration and I'll see what is the probability that the step 3.2 runs at this ith iteration. I claim, and we assume here, that that probability is 2 over I. We're going to prove it in the next video. And then I want to claim that assuming this claim, then the linear time analysis relatively easily follows. And this is using a very nice technique that uses linearity of expectation. So let's go through the argument. Remember that I want to bound the expected running time of this algorithm. Most of the steps are easy. Initialization is, let's say, constant O of 1. Randomly shuffling is O of n. The for loop is, runs in time. This step is O of 1. So the total running time of step 3.1 over the n iteration is O of n. So the only thing that is really mysterious is 3.2. Okay. So so now let's look at this formula. So the expected running time of the ith iteration. So the running time is a sum from I1 to n of the running time of the ith iteration. By the linearity of expectations, I could move this expected value into the sum. In other words, I could switch the order of summation and expectation. And linearity of expectation does not require dependence. So in other words, for every two random variable, a, x, and y, you can always write the expected value of x plus y equals the expected value of x plus expected value of y. That always holds regardless of what the random variables are. So now we're down to this step. We just want to sum the expected value of the ith iteration. Based on this property, the ith iteration with probability with probability 2 over I is something that is not a constant. With probability 2 over I, this step takes I time, right? Because we have to look at constraints 1 to I, but otherwise it takes constant time. So the expected running time of the step 3.2 at the ith iteration is something like this. The probability of it going through step 3.2 times the running time that if it does, and probability of not going through step 3.2 and just doing step 3.1. Okay, so it's essentially just the definition of the expected value. Based on the claim, this is 2 over I. Again, one-dimensional linear program is O of I, and that's essentially works out to this. And if you simplify it, this is just constant. So therefore, on average, the ith iteration takes constant time. So therefore, once you sum over n constants, the total running time is linear. And that's essentially the proof. So if this claim holds, then the proof follows relatively easily. And in the next video, we're going to prove this main